Okay, so this is where I think we left off last time in class. So we'll pick up from here. So we're going to need to be able to convert between diagrams that represent numbers, like, for instance, this number here can be written as 6/10 and 5/100. This diagram is that number. You want to be able to convert between the diagrams, writing out the number in words. So this is 65/100. Get the 65 because it says 0.65. We have hundredths because the last digit in the number is in the hundredths place. So it is 65/100. We can represent as a fraction by we have 65/100. Hundredths are the fractions that have 100 in the denominator. Now we can convert between decimal and fraction, where the number past the decimal point is going to be the numerator, and the denominator is whatever position we're in. If we're in the tenths place, we use 10 as the denominator. If we're in the hundredths place, like this number, we use 100 as the denominator, and we go from there. This is usually not going to be a simplified fraction, but we can simplify the fraction um, by looking for factors of 2 or 5 to cancel. There may be larger factors, but um, if you feel like checking for 2s, 5s, and 10s is easier than checking for other things. So those and those will always work. If you cancel out all of the 2s and 5s, you will have a reduced fraction in this process. So if you want to check for bigger factors and cancel down faster, that's fine. But if you want to only look for the smallest number of things to check, checking for 2s and 5s will also work. So with this one, with this 65/100, we check 2 doesn't go into 65, so we don't have to check 2 anymore for this problem. 5 does go into 65. 5 also goes into 100, so we will cancel that. 5 goes into 65 13 times. 5 goes into 120 times. And now the top is not divisible by 5. We already didn't, we already checked off 2s. We don't need to check it again. But for completion, 13 is not divisible by 2. So we are done. This is the reduced fraction, the answer to part D. Okay. So let's do some of these. This one we're just writing as a fraction and then simplifying. So this here we have, this is in the thousandths place. We put 1,000 in the denominator. The numerator is just going to be that number. I'll show you how to handle numbers with a whole number part that's not 0 later. We have this. We want to cancel out 2s and 5s. The numerator is not even, so that means there are no 2s to cancel. But there is a 5 to cancel. So when I cancel 5 from the top, I get 21. When I cancel 5 from the bottom, I get 200. This is not divisible by 5. The original wasn't divisible by 2, so now we are done. This is the final answer. If you do have a number on the left of the decimal, that's perfectly okay. The denominator will still be determined by the smallest digit, the smallest position. In this case, we have 10 thousandths, so we'll put 10,000 in the denominator, and I should probably give myself some more space. We'll start writing over here. There's 10,000 for the 10 thousandths place. Now I'm going to write this number without the decimal point. I have 30,771, which is not divisible by 2 because the top is odd, and it's not divisible by 5 because it ends in a number that isn't 0 or 5. So this is completely reduced as it is. With this, with the negatives, we just put a negative in the front of the fraction, or on the top of the fraction, or on the bottom of the fraction. This is in the thousands place, so we put 1,000 down here. We have 36 of them. That looks good. To reduce this, we see that the numerator is even, so we divide by 2. We might notice that we can divide by 4. If we want to divide all of the factors at the same time, we can divide by 4 and get 9 over 250. Although if we don't want to check things bigger than 2 or 5, we can say that this is 18 over 500. Numerator's still even, divide by 2 again, and get the same answer. Oh, and keep your negative signs. Okay, comparing rational numbers. This is done using what's called dictionary ordering. So when you're putting words in order, you check the first letters first, then you check the next ones, and then you check the numbers or the letters after that. With this, we have to do the same thing, but first we have to line up the decimals and maybe fill in some zeros. So, well, negatives are always less than positives, so that's why we have the number sign or the inequality going that way. Over here, I'm going to write these numbers on top of each other, and I'm going to line up the dots while I do that. If we start from this side, the left side, and work this way, I see that the first digits are the same. That means that I need to move on to the next digits. And I see that there's a difference. This one here is bigger than this number here. That means that this second number is bigger. Sign goes that way. Same idea here. 7.018. I look and those are the same. These are different. This one is bigger. Writing it okay. Have 7.018, 7.180. Those are the same. These are different. This one's bigger, so the sign goes toward this number. That one is bigger. 7.180 or 7 and 18 hundredths or 7 and 180 thousandths is the way that it looks with the 0 here. By the way, if there are trailing zeros, you should delete them before you write out the English word for the number. I don't think the computer will like it if you said that this is 7 and 180 thousandths. I think that it's going to ask you to put it as 7 and 18 hundredths. Okay. With this one, if we line up the numbers, negative 7.9, negative 2.18, we look at the first digits, we notice this one is bigger, but because these are negative numbers, a bigger magnitude negative number is going to be further from 0 in the negative direction. So if this is 0, this is where 2.18 is, and over here is where negative 7.9 is. So this one has the arrow going that way, where negative 2 is bigger than negative 7. By that we mean that if you only owe $2.18, you have more wealth than if you owe $7.90. This is similar to the ones we just did. We're gonna have to make comparisons so that we can put all of the numbers in order from smallest to biggest. So looking at this here, um, first off, all of the negatives are going to come before the positives. I have a 0, a 0, and a 0, and a 6. So this one has a bigger number. The 6 is bigger than 0. And because they're both negative, that means that that 6 puts negative 0.62 before negative 0.060. Those two are now taken care of. Now we look at the positives. Well, this one has a 0 here. This one has a 6 here. So this is going to go to the right of this number here. And then this one has a 0 here. So we're going to compare this number and this number. See that this is 0.062. That's going to come after 0.060. You can always add a 0 to the end of a decimal because in some sense there are infinitely many zeros following this anyway. Those zeros mean that you don't have any pieces that are that small, but not writing that you have pieces is equivalent to that. So that means that we have 0.06 comes next, 0.062 comes after that, and the very last number we have is 0.6. Those are all in order. Same thing here. The negatives will come before the positives. You'll probably want to change everything into decimals first on this problem. Negative 0.5, negative 1, negative 0.3, 0.55, 0.5, negative 0.2, and 0.2. We have these numbers. The negatives will come first. So we compare these. Negative 0.5 has a 0 in the ones place. Negative 1 has a 1 in the ones place. So that means that of the two that we're looking at right here, that one is going to be more negative. So looking over to the next one, here this 0.3, that is, it has a 0 in the ones place, so this is going to be less negative than negative 1. So that means that we have to compare this number to this number. 0.5 is bigger than 0.3, so that means this number is less negative than this number. So putting all that together, we get negative 1, negative 0.5, negative point. Then it looks like we have another negative number here, negative 0.2. The 2 compared to the 3 is less negative, so we have negative 0.2. That takes care of this number, this number, this number, and this number on our list. That one. After that, we look at the positive numbers. See that 0.2 is smaller than 0.5, and this is also a 0.5, so the 0.2 comes next. That number taken care of. 0.50 comes before 0.55, so we get 0.50, 55, and then we can convert all of these back to their fractional form if we want to. Let's see what the question says to see if that is what we want to do. It doesn't say we have to, so I think that we can leave it as decimals. So I told you in class that fractions are really good for multiplying things together, but decimals are really nice for adding and comparing. Often, if you want to compare if two decimals, sorry, if two fractions, like which one is bigger of the two fractions, converting to a decimal is a pretty good way of doing it. Although we learned a different way to do it before we started talking about decimals in class. Okay. So, evaluating square roots. So, some square roots are going to be really nice because they are taking square roots of perfect squares. We know that 11 times 11 is 121, so that means the square root of 121 is just 11. Nice. Um, some fractions even have nice decimals. Sorry. Some fractions even have nice square roots because the numerator and the denominator are both perfect squares. 4 times 4 is 16, and 7 times 7 is 49. So that gives us a nice reduced 4/7 as our square root. When the negative is on the outside, we just carry it over because square roots count as exponents in the order of operations. So the exponents come before multiplication, and the negative sign counts as m, as multiplication. It counts as that because it is that, but that means that you're going to do your square root first because that counts as an exponent. It is an exponent. It's a 1/2 power. Before you do the multiplication, which is multiplying by -1, that's what the negative sign means. So if the negative is on the outside, you're going to take the square root first, then multiply by -1 and get your answer. If the square root is on the inside, the way you want to think about that is that not only is the square root uh, an exponent, but it's also a grouping symbol. So it acts as parentheses around whatever number you're taking the square root of and a 1/2 power. So if you have the negative on the inside, like in this problem here, this is the same as we have parentheses around 100, -100, and we're doing a 1/2 power. In the order of operations, now we have grouping symbols. We have parentheses, meaning that we have to first multiply the 100 by a negative sign to get a negative number. And then we are taking the 1/2 power, which is square root. And you can't take the square root of a negative number, at least not in this class. Um, we're not doing imaginary numbers in this class, so we won't worry too much about that. I will say that there are some really nice engineering applications to imaginary numbers. So they have a use. We won't discuss them in this class, but whenever you see the negative on the inside, this is non-existent. We think that they ask us to write DNE. Yeah, so I have a little bit of problem with that particular statement. DNE, in this case, I would use that for limits, but our textbook uses DNE, and I'm not going to introduce other notation and be confusing. So this one doesn't exist. The negative is on the inside of the square root. On the other hand, the negative on the outside of the square root is fine. We're going to first take the square root of the top and the bottom. 5 times 5 is 25. 8 times 8 is 64. And after we take the square roots, we're going to put a negative sign. The exponents come before multiplication and division, PEMDAS. Same thing here. Square root of the numerator is 1. 1 times 1 is 1. Square root of the denominator is 2. 2 times 2 is 4. This here have 81 is 9 times 9, so the answer is, or the square root is 9. Then we multiply by -1 to get -9. This one here, I know that 11 times 11 is 121. This is a little bit more complicated. If I do 0.11, if I do 11 hundredths, that's going to end up being the square root. I can check that by multiplying 0.11 by itself. First off, 11 times 11 is 121. Second, you have 4 digits that are to the right of the decimal. So I need to have 4 digits to the right of the decimal, and I need to fill in a 0 to make that happen. Notice that this number and this number are the same. So, and this number and this number are also the same, and that means that this is the square root. You're going to do a similar thing for 0.04. Now, those are nice numbers that are called perfect squares. Most numbers are not perfect squares. So we have to figure out how to deal with square roots when we are not taking the square root of a perfect square. For instance, if we want to take the square root of 2, well, I know that the square root of 2 has to be less than 2, but it also has to be bigger than 1. So I'm going to pick a number that's between 2 and 1 and make a guess. For instance, I can guess, what if 1.4 is the square root of 2? Then if I square 1.4, I should get 2. Certainly, I get pretty close. I get 1.96. 1.96 is a perfectly reasonable estimation of the perfectly reasonable approximation of 2. Well, calculator. Now, we could just hit the square root 2 button on a calculator, but that doesn't tell us a whole lot about what square roots are. If I type in 2, just hit square root, I get an approximation. What we're going to do is we're going to see one way of getting an approximation that, before calculators, people would have to find these square roots by hand, and this is one way you can try it. Say, oh, 1.4 is a little bit too small. When I square 1.4, I get 1.96, which is less than 2. Well, what if I pick 1.5? I'm going to write it on 2 lines because my pen is a little bit thick. But what we want you to do is fill out this chart with guesses. Say, oh, 1.4 is too small, so I need a bigger guess. I pick 1.5. If I multiply 1.5 by 1.5, I'm going to get 2.25. That's too big. So I need to get something smaller. Well, what's between 1.4 and 1.5? Well, 1.45. And we're not going to make you do these multiplications by hand, although that would be great practice for your multiplication skills. But if you choose to use a calculator to do these multiplications, we are okay with that. So I'm going to multiply 1.45 times itself. I guess I could use the square button. For everything. 1.45 5 squared gives me 2.1025. Our goal is to find a number that when I square it gives me 2. I got something too big. I got 2.105. Round that. So, since I got something too big, I'll go smaller. Let's pick 1.43. That seems between zero point 0.4 and 0.45 is 0.43. So I get my calculator. I'm going to try that now. Type in 0.3, 1.43 square, and I get 0.0449. That is still too big. When I round it becomes 2.045, and that's about as many digits as I can fit. But I want you to go with your calculator and try and dial in. Whenever your square becomes smaller than 2, guess bigger. Whenever your guess is bigger than 2, guess smaller. And you do that until you fill out the chart, and you should get something that's close to this when you're done. 1.4142136. So after doing that, you're going to try and square whatever your calculator approximation of square root of 2 is. You're not going to let it store its memory, so you're going to write down the number, clear the calculator, type in the number, and hit the square key. And it should give you a rounding error if you do that. It shouldn't be exactly 2. And the reason for that, you will have to try and explain, and we can talk about it in class. Okay. So, with that, let's talk about rational numbers. The definition of a rational number is that it can be written as a form a over b, where a and b are integers. So, like 2/3 is a rational number. It can be written as 0.66666 repeating forever, or it can be written as this nice fraction, where the numerator is an integer, the denominator is also an integer. On the other hand, the square root of 2 is not an integer, it's an irrational number. It's about 1.4, but it goes on forever. And there's no way to write it as a number, sorry, an integer over an integer. It doesn't exist that way. There is a proof of that. I might show it to you in class. So if you take all of the rational numbers and all of the irrational numbers together, you form what's called the real numbers. And if you put them in a line, you get what's called the real number line. We're going to look at these and determine if the numbers are rational or irrational. Basically, if they stop, then they are rational. If they don't stop, they are irrational. So, square root of 121 is 11. I can write that down without an infinite decimal. That's great. Square root of 14, I get this thing. Goes on forever, and that's going to be irrational. This one is rational. This one is irrational. And you go through all of them. So this one here, this one repeats. It's 0.02454545 forever. That's what this bar on top means. And so the ones that repeat the same pattern, those are going to end up being rational too. I might show you that in class, but I probably won't. Um, if it stops, it is rational. If it goes on forever, but it repeats the same pattern, then it is rational. Just like how we had 2/3, when I write it as a decimal, it repeats 0.666666666. Repeating is fine for being rational. On the other hand, some numbers like pi do not repeat, but they do go on forever, and those are irrational. And any of these that you want me to, we can go over in class. And let's see, we've been going for half an hour. Um, this might be approaching the amount of time I have today to record. So we will talk about approximating square roots though. So let's write down all of these squares. 1 times 1 is 1. You can pause the video and write these out by yourself and then see if you get the same answers I do. So I'm going to go through these. 3 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49, times 8 is 64, times 9 is 81, 10 times 10 is 100, 11 times 11 is 121, 12 times 12 is 144. Now, these are the perfect squares from 1 to 12. Anything that's not a perfect square is going to have an irrational square root. But the nice thing is that those square roots will fit between the numbers 1 to 12. So what I mean by that is like, if I want the square root of 10, well, 10 is between 9 and 16. My 9, here's my 16. So the square root of 10 is bigger than the square root of 9 and smaller than the square root of 16. But the square root of 9 is 3. The square root of 16 is 4. So that means that 3 is less than square root 10, which is less than 4. I now know that square root 10 is between 3 and 4. It's 3 point something. And that works for any square root. Any square root, you can always take a perfect square below it and above it, and now you know, hey, my square root is between those two numbers. Square root 5, well, I know that 4 is less than 5 is less than 9, which means that square root 4, which is 2, is less than square root 5, which is something, which is less than square root 9 is 3. So I know that the square root of 5 is between 2 and 3. And I can plug it into a calculator and round to the nearest hundredth. Square root of 120, well, I know that 100 is less than 120, less than 121. So that means square root of 100 is 10, is less than the square root of 120, which is less than 11. So it's 10 point something on the calculator. You can plug those in yourselves. Any of you want me to do in class, I can do. That makes us done with 6.2. Yeah, that's a good place to wrap for today. Tomorrow we'll start with a recording on 6.3. So, best of luck to all of you. Hope the homework is going well. Send me any questions you want me to answer in tomorrow's video, and I will see you next time in class. Bye.